This is Mike, and I am a tutor with Chegg Tutors. And today I will go over with you a topic called a recursive binary search. And this is a topic in computer science, particularly in searching. So um, before we get to that, we'll try to frame the problem that we're going to solve, like what is recursive binary search and where is this used. So we'll try to frame an example problem. We'll try to think about a few ways that we can solve this sample problem. We'll just analyze the problem, and we will focus on one particular way of solving a search problem using a method or using what's called recursion, and so we'll talk about what recursion is, and we will use recursion to kind of go back and solve this binary search problem. So let's jump right in. So here is an example. So let's say that you have full of integers. Let's stick with integers, and let's say that given this array and a number x, we want to find where x is located in that array. So for example, let's say that we have 15, and I would like to say, okay, can I find where 15 exists in this array if it exists? So that's the problem here. We're trying to search essentially for something in an array. And so there's one other note to that we should notice about this. And so let's consider arrays whose entries are effectively sorted. So if you take a look here, you might have already noticed this, but these numbers are all sorted in ascending order. And so to actually do the sorting, that's a different topic. So we're going to assume that we have a sorted array and going to see, can we find something in this array? So for example, yes, 15, we see that it's located here. So we want the position it's located. So assuming that we start at index 0, the position where this is located is 4, right? Okay, so that's the problem that we want to solve. Find a number in a sorted array. So let's try to think of a way that we can do this. A simple way that we can do this. So let's, I guess, think like a computer. So if you're a computer, then basically what you have to do if you want to find this number, one way you can do it is to basically go through one by one and see where 15 is. So you start here at the first index, you kind of move one by one and compare. So is it 7? No. Is it 8? No. Is it 10? No. Is it 15? Yes, it is 15. So this is index 4. So then I should return 4. So that's a simple way of solving this, and it works. But we will see that it's not necessarily the best way to do it, because there might be faster, more efficient ways to do it. And that is where a recursive binary search actually comes into play. So let's talk about that a little bit. Before we talk about that, let's specifically talk about the computer science concept of recursion. So recursion basically refers to a way of solving a problem. So specifically it says here, a way of writing a function where inside the actual definition of the function when you're writing it, this function that you're writing itself is used / called. So when you're writing a function, you basically, let's say the function was called find. Somewhere in that function, you're going to call the find again, and it's going to call itself essentially. So if you haven't seen this concept before, it might seem a bit strange. First off, you might think, can you even do that? You're writing this function, how can you call it? It turns out you can call it. And so it might seem cyclical, and also you might think, why would you ever want to do that? So it turns out that there are lots of problems that you can solve quite elegantly, and you can write quite succinctly, writing a function recursively versus not. So that's the reason why you want to do this, even though it might seem a bit strange or difficult. But in order for you to use recursion though, so the trick in thinking about a problem and solving it recursively is to break down the problem you have into smaller problems, basically, where each smaller problem is logically identical to the original problem being solved. So let's see what we mean by that, just by example, with the same array here. And let's look specifically at recursive binary search. Okay, so let's try to solve this in a different way. So in order to do that, let me frame this. So let's say that we have this position here. Let's call this the lower position. It's just the first entry. You know, we have the last entry. That's easy to get as well in most programming languages. This is, let's call it upper. And let's say that we're trying to find 15 again. Okay, so let's think about another way to do this. How about we try to, so let's exploit another fact that we actually did not exploit before, that the fact that these numbers are in order. Remember that? So we can utilize that. So in order to do that, let's say that we split this array into two. So if you imagine, you can kind of split it like this, right? But let's think a little bit more discreetly. This is kind of in between these two values, and so anytime you want to refer to specific items or entries. So let's say that just arbitrarily, let's move one below the middle point, and let's call this the midpoint. So effectively split it into two. So let's notice something here. So let's compare this number at the midpoint to the number we're trying to find. So 10 is less than 15. 10 is less than 15, right? So what can we say about this? We can actually say that if this number here is less than the number that we're trying to find, it must exist, it must be the case that the number is in the second half or the greater half of this array. And conversely, if this number is greater than this number, again, because it's an order, this number must exist in this first half. So if it's smaller, for example, I'm trying to find 6, it must be in this first half. And if the number is equal to the number we're trying to find, obviously, then that we found the number, so we're good. So we effectively subdivided. So in this case here, 15, so based on that rule, we know that it must exist in the second half of the array. So you can think of it this way. So there's no point in looking here, right? There's no point in looking here. We can just look at this portion here. Okay. So once we enter this portion here, so let's rename this lower now. Notice here, we are looking at a subarray, but we can think about this problem the same way as we thought about the problem for the entire array, right? So let's try to do it again. Let's try to subdivide this. So then, by convention, the midpoint would be here. And so we need to compare this. So 15 is less than this number, right? Hence, we can ignore this part here. It must exist inside this subarray. I mean, obviously we see that, but let's go through it step by step. So it must not be in here. It must be over here. So then let's take a look at just this portion. Again, same problem, right? We have an array and we want to find the entry in this subarray. So now, this here is now the upper, right? So the midpoint here, by convention again, will be here. And what do we notice here? The midpoint value and this value that we're trying to find is the same. So we found the position of this value. We found it. So this is basically what I described here is essentially recursive binary search on this particular integer array. So that's the strategy. So before we can write this in code, let's think about, there's a couple other things that I should mention about recursion that we need to keep in mind. So recursion requires a couple things. It requires a couple things. So first, what it requires is it requires a base case when you're writing a recursive function. So the base case is essentially the smallest possible case that you can think of. So for example, somewhere in your code when you're writing this recursive function, you need to take care of these cases. For example, what if you have an array or a subarray that's essentially just one entry? Let's say, 17. And I'm trying to find 15 in this array. Seems kind of trivial, right? But 15. So how do we test this? Is 15 inside of this? No, it's not. It's a 17. So that means it doesn't exist in there. If this were 15, then we say, oh, it's 15, and so it's just this position. So that's the base case. It's the smallest possible case. So the second thing that recursive functions require is basically what we just described here. So this is the general case. So that's solved by subdividing the original problem into smaller problems. So here we subdivide it into two pieces, right? And we see which one it's in, but where each smaller problem is of the same form. So when we divide it into two pieces, we saw that in this green piece, we can treat it, once we get rid of that first half, we can treat this just as this kind of you're starting over, right? You're just finding it within that subset or the subarray. So with that in mind, we are ready to put all this together into code. So let's try to do that. Let's go to the code editor, and I'm going to write this in Java. So let's first start with the function definition. So this will be public static. So it's going to return an integer, right? Because remember, we're trying to find the position or the index of where it's located. So it's going to be int, or it's going to return -1. I guess let's say that it returns a -1 if it can't find the array of numbers, right? So let's call that int bracket array. We need to pass in the number we want to find, right? So also what we're going to have to pass in is we're going to have to pass in the lower and the upper bounds. That's those two. We started off with at the first position 0 and at the last position length -1, right? And we'll soon see why exactly this is necessary. Okay. So when you write this function, first off, we need to remember those 2 points, right? We need to take care of the base case first, and we need to take care of the general case. So let's write a little bit of pseudocode first. So the base case, so what is that the case? So basically if there's only one entry, right? So what do we mean by one entry? Specifically what we mean here is, remember that this array, we can be dealing with a sub-array, right? But then it's a sub-array within a bigger array. So how do we know when we have just one entry? We know that one way we can tell that is if the midpoint basically corresponds to the lower and the upper, or if the lower and the upper are the same, right? So they correspond. So basically, it's just one entry, right? So then basically, we need to test, right? If the entry is equal to x, then what do? Then you return it, right? Return the index. Actually, we return the index. So lower or upper, either one's fine. So what if it's not this one? Remember, this is the base case. This is the case where we only have one box, right? We're referring to just one box. That's our subset array. So then if it wasn't equal, then it's not there, right? So then at this point you can just return, else, I guess we could say that, then return -1. So -1 is our way of saying we couldn't find it, or it doesn't exist in this array. So that's our base case. Okay? So again, just to reiterate, the base case is where we're only looking at one entry, right? Our subarray has been reduced down to just one box. And so how do we test that? We test if it's one box, if the lower and upper happen to point to the same box. Okay, so now let's deal with the general case here. Okay, so there can be 3 cases here for the general case. So before we do that, let's go back to the whiteboard and let's try to see what we did here. Anytime we had a lower, upper in a subarray, or this original array, we had a lower and an upper, we first wanted to compare the value at the midpoint to the value we're trying to find, right? So we need to first compute that. So compute the midpoint, right? So given that midpoint, so what do we want to do? We want to test if the value at the midpoint is the value I want to find. Okay, good, we're done. We just return that index. If it's what? If the value at that point is greater than that value, then we need to look at the left side. Otherwise, we need to look at the right half of the array, right? So So let's take care of those three cases. If array midpoint, right, is equal to x, then what do? Then we return that, right? And we're done. Return the index. So basically, I guess we can be even more specific. The index point is strictly greater than x, right? Then what do we need to do here? So this is actually where the recursive call is going to happen. Because if the array midpoint, so this value here, the array midpoint is less than this value. So actually, which one am I coding here? So let's flip this. If this value is less than this value, we need to look at the second half, right? So basically, we need to find this in only the second half of the array. So find x in the second half. So else, so if it exhausts those other two conditions and it's not true, then you find x in the first half, right? So you could also do like an else if. Oh, so we should do an else if here. So we can also do an else if and test if array midpoint is greater, but just do an else because we covered all the cases and logically it's the same. So let's fill in all of these things, basically. We're done with the pseudocode. So if lower and upper are equal, right? So equals upper. Then we need to test what? We need to test if, so let's put these in brackets. If the entry is equal to x. So what is the entry? So remember, we always have to refer array at what position. If lower upper is equal, it doesn't matter. We can just use either one. Array lower is equal to x. That means we found it. So that means that we return the index. So the index can be either lower or upper. It doesn't matter, right? Else, so I guess we can get rid of the comments here because that's essentially the same. Return -1, signifying we could not find it. So now let's do the general case. So that takes care of the base case. Let's take care of the general case. So let's compute the midpoint first. So let's do int midpoint is equal to, so how would we find the midpoint? Essentially, I guess from algebra, it's like the length divided by 2, right? So it would be what? Upper minus lower divided by 2. And so one thing to note here is I declare this as an integer. So if you divide something by 2, it's not necessarily an integer, right? But it will save it as an integer because the type is integer. So it'll give you the behavior that I was describing before. So if the midpoint ends up being somewhere here, it'll round it down to the next integer there. So it works the way that we wanted it. Okay, so let's write this one out. If array midpoint is equal to x, so if array midpoint is equals to x, remember 2 equals, then we found it at that midpoint. So return the index of that point. So basically you can return midpoint. Else, if array midpoint is less than x. So here, this is the cool part. So what did we say here? If it's that point is less than the point that we want to find, it must exist in the second half, right? So how do we find it in the second half? This is where you call it on itself. So we find the x. So remember, we need to follow the function prototype exactly. So array, still the same array, still the same x. We're not changing what we're trying to find. So what we need to change is we need to change the lower and the upper bounds to kind of specify the sub array that we're looking in. So we need to find it in the second half. So what does that mean? So the upper is going to remain the same, right? Sorry about that. So upper is going to remain the same. So upper. But then the lower one is going to be what? It's not going to be, for example, if you take a look here, the lower is not going to be here anymore, right? Assume that we are starting with this big array. It's not going to be here anymore. You want the lower to be here now, which is basically just the midpoint plus 1 position over, right? So what you're going to pass into here is the midpoint plus 1. Okay, so else, so find x in the first half. So this is where the comparison went the other way. So array x. Again, here, if it's in the first half, the lower index is not going to change, right? So it's going to be lower, but the upper one is going to change. So what would that look like? So the upper one would actually, so let's say it happened to be inside here, then the upper would have to be midpoint, right? So we can put midpoint in, but note that we can do a little bit better than that because we know that it's not here, right? Because if it were here, it would return that value because it found it. Because it didn't find it, it means that it can't be that midpoint. So you can omit that and just do, essentially, just do this. So it's just a slight more efficient way. So that would be m minus 1, right? Because it's 1 over to the left. So it would be midpoint minus 1. Okay? So basically that's it actually. So we've written a recursive way to search this sorted array and find an entry. And so just to recap here, remember any kind of recursive function, we need a base case and we need a general case. So this base case this is essentially what allows the recursion to stop, because note here in line 26 and 29, you're calling the function itself. So what prevents it from keep going on forever, right? Well, there's two things. One is basically that you have a base case. When you hit the smallest possible case, okay, you got to decide something now, right? Because you're only at one number. It's either that or it's not. So that's what we took care of here. And here, basically, we took care of a problem where we broke it down into two smaller chunks, and each chunk, basically, we can treat it as if it's the same exact problem on the original one. It's just a subarray. So we need to modify the lower and upper. So now, actually, one final note. It should now make more sense why we need these int lower and int upper as parameters up here in line 1. The reason why we need that is because we're calling this function on itself. So we need to always keep track of, in the subcalls, which subarray that we're referring to. So when you originally call this find function, you're going to set lower and upper to what? You're going to set it to 0, and you're going to set it to the length of the array minus 1 to kind of start the search at the entire array. Okay, so that basically concludes this. So thank you for tuning in. I hope you found that helpful. Recursion is a topic that is difficult to grasp. I find that a lot of students struggle with that, and I struggled with that in the beginning as well. So I hope that this helped, and I would suggest that try to rewrite this function recursively on your own without looking at these notes once you look through this video and see if you can do it. And if you can, that's great. You've basically learned recursion. So yeah, so if you enjoyed and found this informative, please check out my profile on Chegg Tutors and get the link given here. I tutor various computer science topics, but I also tutor statistics, machine learning, lots of mathematics, and it goes on and on, basically, the list. So